Hello, my dear students. Welcome you all to Shri Jaindra Rank Zone classes. I am your mentor and your friend for the subject chemistry, and I will be taking the organic chemistry. My dear students, we have started biomolecules and we have started the study of carbohydrates. We discuss about the structure, the classification, the chemical properties. Today I am going to start with the cyclic structure of carbohydrates, especially the cyclic structure of glucose. So let us start with the cyclic structure of glucose. Cyclic structure of glucose. There are some properties or there are some facts which are in favor of that glucose is having a cyclic structure. These evidences, they say that glucose in its stablest form shows the cyclic structures, not the open chain structure. Okay. Although the open chain formula of glucose, it explain most of the reactions. Okay. So what are the favorable points for cyclic structure of glucose? Favorable. Okay. First point, glucose is having an aldehydic group despite of having any aldehyde group. It does not react with sodium bisulfite, NaHSO3, and hydroxylamine. Sodium bisulfite and hydroxylamine. Hydroxylamine reaction I will tell you later when I will explain the pentacetate. The first is, despite of having an aldehydic group, it does not react with sodium bisulfite and ammonia. Okay. The reaction with sodium bisulfite is an addition reaction which gives a white crystalline products. Okay, when the aldehydic group reacts. So although it is having an aldehydic group, but it doesn't show the addition reaction with sodium bisulfite, and neither it reacts to form aldehyde ammonia with reaction with ammonia. Glucose does not give Schiff's test and test with 2,4 dinitrophenyl hydrazine 2,4 DNP test, which is a characteristics test for aldehydes. So it does not undergo the 2,4 DNP test, okay, like other aldehydes. Neither it give the Schiff's test, mean neither it form the imine, no imine formation. Okay. Third, it does not react with organometallic compound like metallic compound like Grignard reagent. Fourth, when we react glucose with acetyl chloride, it forms glucose pentacetate. Glucose pentacetate does not react with hydroxylamine. This is the reaction I was actually talking about. With hydroxylamine. Okay. So the pentacetate of glucose did not react with hydroxylamine. Okay. Glucose basically exists in two isomeric forms, alpha and beta. Isomeric forms, alpha and beta, which are obtained by heating glucose with methyl alcohol. Obtained by heating glucose with methyl alcohol. So glucose, it exists in two isomeric forms, alpha and beta form. Okay, obtained by obtained by crystallizing obtained by crystallizing glucose from the concentrated or saturated aqueous or alcoholic solution at 303 Kelvin. So glucose exists in two isomeric forms. This is the D-glucose, which exists in two isomeric forms, alpha D-glucose and beta D-glucose. The forms, they are crystalline in nature and they have different melting points and optical rotations too. When their optical rotations are different, okay. So when glucose is crystallized from its concentrated aqueous solution or alcoholic solution or solution with acetic acid at 303 Kelvin, we get these two forms, okay. We get these two forms, okay. So basically, I should say that at 303 Kelvin, okay, there is a form which is obtained as alpha D plus glucose, alpha D glucose, okay. The melting point of alpha D glucose is 419 Kelvin with the specific rotation of 110 degrees, okay. Then the beta D glucose form is having a melting point of 423 Kelvin with a specific rotation of 19.7 degrees is obtained by crystallizing glucose from hot and saturated aqueous solution of at 317 Kelvin. So this form is basically obtained by crystallizing glucose from hot and saturated aqueous solution or pyridine solution at 371 Kelvin. So at 371 Kelvin, beta D glucose form is obtained. At 303 Kelvin, alpha D glucose form is obtained. Okay. The melting point of alpha D glucose is 419 Kelvin. The melting point of beta D glucose is 423 Kelvin. The specific rotation of alpha D glucose is 110 degrees. The specific rotation of beta D glucose is 19.7 degrees. Okay. Now, mutarotation. It's a very important term. Either of the two forms of glucose alpha D and beta D are dissolved in water in aqueous solution. Okay. So the aqueous solution of alpha D and beta D glucose, when allowed to stand, they are converted into the other forms. So when two forms of glucose, these alpha D and beta D glucose, when allowed to stand, they are converted into other form. Okay, they are converted into other form. An establishment of equilibrium mixture of both the forms, that is alpha D glucose 36% of yield rate and beta D glucose. Okay, so the alpha D glucose is converted into a beta D glucose. The specific rotation of alpha D glucose decreases from 110 to 52 degrees. Okay, it decreases from 110 degrees to 52.5 degrees. And in case of beta D glucose, it get increased from 19.7 to 52.5. It increases to 52.5. Okay, so this is the mutarotation. Mutarotation is basically interconverting of alpha D glucose into beta D glucose. Okay, the specific rotation, okay, falls up on a constant value of 52.5 degrees. The alpha D glucose specific rotation decreases from 110 to 52.5, and beta D glucose it increases from 19.7 to 52.5. Now, this feasible change in the specific rotation of an optically active compound within time. So, if I have to define butarotation as the spontaneous conversion or the change of specific rotation of an optically active compound with time to an equilibrium value is called mutual rotation. Okay, so there is a equilibrium mixture between these two forms. How? Alpha D glucose specific rotation plus 110 degrees. Okay, it is converted into open chain which is very much unstable. For a transient time, it is converted into 52.5 degree of specific rotation. Okay, then it further converts into the beta D form with specific rotation of 19.7 degrees. Okay, so this is the conversion of a cyclic form into a straight chain form or an open chain form, an open chain form into a cyclic form. Okay, if I have to show you the picture, so basically the compound which is formed in the form of alpha beta D glucose, it is a simple chemistry. It is a cyclic hemiacetal which is formed according to the fissure between the carbonyl group of CHO and the hydroxyl group of the fifth carbon. Okay, so formation of a stable cyclic hemiacetal between CHO group and OH group. Formation of stable cyclic hemiacetal. Okay. Now, the next reaction is that glucose, it forms isomeric methyl glucosides. Glucose, it forms isomeric glycosides, methyl glycosides. Okay, so whenever the glucose is heated with methanol, so when glucose is heated, okay, with methanol in the presence of dry HCl gas, dry HCl gas, okay, it gives two monomethyl derivatives which are isomers. Okay, continue. The above reaction produces monomethyl derivatives. Okay, that is methyl alpha D glucose, not glucose, glucoside. Okay, and beta methyl or methyl beta D glucoside. Understood? So this is the reaction in which the glucose forms isomeric glucosides. Okay, methyl glucosides. Two of these glucosides, they actually don't reduces the Falling's solution. The above glucosides do not reduce Falling's solution. Okay, so it means all the reactions which are due to the free CHO group, it confirms that CHO group is not free and is converted to COOH, carboxylic acid. Okay, is it clear? Yeah. Now we are going to discuss about the in detail the next slide. The cyclic structure of glucose. Okay. So in the previous slides, we basically collected the evidences which says that the glucose is not having the open chain structure, it is having a closed chain structure. Okay. Now, the cyclic structure of glucose says what? That D-glucose, it exists in two optically active forms. D-glucose exists in two optically active forms. Understood? Okay. These two optically active forms, okay, they are actually the hemiacetals. Okay, they are actually hemiacetals. So these forms are known as what? Alpha D glucose and beta D glucose. Understood? These two forms. Okay. Now, glucose forms hemiacetal between the CHO group and the OH group. Okay. So it becomes the C1 first carbon are having CHO group and the C5 of the OH group. They make a cyclic hemiacetal form, okay, according to the pyranose. Okay, so the result of this, the first carbon having the CHO group becomes asymmetrical or chiral carbon. And the OH group which are formed may be either on the left or on the right in the Fisher projection formula. Okay, I'll explain. So the basic carbons which are involved to form this cyclic structure, okay, is basically the first carbon, that is CHO group, and the fifth carbon, that is the OH group. Okay, the C1 carbon after adding the OH group according to the Fisher projection formula becomes asymmetrical or chiral carbon. Now, what will happen? The two isomers which are formed are different in the orientation of hydrogen and OH around C1 atom, means the first carbon. Okay, so this carbon, okay, which is at this first carbon in the first position having the H and OH group. So the orientation of this H and OH group, okay, basically gives the alpha D glucose and beta D glucose. Okay, the isomer, if the OH group or the hydroxyl group is on the right side, it is alpha D glucose, and if it is on the left side, then the beta D glucose. Alpha D glucose and beta D glucose. Understood? Now I'll show you the picture. This is the carbonyl carbon. OH. This is the first carbon, second carbon, third carbon, fourth carbon, fifth carbon, and the sixth carbon. So what basically is happened, the oxygen is having the lone pair, the fifth carbon. Okay, this is the D glucose open chain form. Okay, the bond will shift here as a pi electron cloud will shift on this oxygen. This oxygen will acquire the partial negative charge and the carbon will acquire the partial positive charge. To compensate the partial positive charge of the carbon, the lone pair will undergo the nucleophilic addition on this carbon. The nucleophilic addition on this carbon. Okay. So this oxygen gets added to the carbon. Okay. Or we can say that both of these carbon are basically added with this oxygen. Both of these carbon are basically added with this oxygen. This hydrogen attacks the more electron densile oxygen. So this attacks here. Now the two forms which are obtained like this. Carbon, this is OH, second carbon, third carbon, fourth carbon, fifth carbon, and the sixth carbon. Previously, in the open chain form, we were having carbon number 2, carbon number 3, carbon number 4 and carbon number 5, which I should say they are the stereocenters, or they are the asymmetric carbon atoms. Okay, so these carbons, second, third, fourth, and fifth, they are the asymmetric carbons. But now you can see the first carbon as well, it becomes the asymmetric carbon. This is the first carbon, second carbon, third carbon, fourth carbon, five carbon, and six carbon. Now you can see the first carbon is having one, two, three bonds. The fourth bond will be the oxygen. Fourth bond will be the oxygen. Okay. Now here, the 1, 2, 3, 4, 5, and 6, right? So here you can see this first carbon is considered to be the anomeric carbon. Along this anomeric carbon, we are judging the position of these hydroxyl groups. Right side, alpha D, left side, beta D. Okay, these are the two forms. So you can see the pair of optical isomers differ in the configuration only, okay, around the first carbon, around the known as anomers. These are known as what? Anomers, or the anomeric carbon. Most importantly, these forms are not enantiomers. Enantiomers means they are not superimposable mirror images. Okay, they are not mirror images of each other. Okay, they are not enantiomers. They are not mirror images. Non-superimposable mirror images. I hope you got it. Okay. So this representation is known as what? The above representation, what we have done. This representation is known as what? Fisher projection formula. This is known as what? Fisher projection formula. Okay. Understood? These are the Fisher projection formulas. All reducing carbohydrates that is, if they are monosaccharides, then well and fair. Like glucose and fructose. If they are disaccharide even, maltose and lactose also show the above behavior. Mean show muta-rotation. They undergo muta-rotation. Okay, reducing carbohydrates, they also undergo muta-rotation, whether they are monosaccharides or whether they are disaccharides. So my dear students, we discuss about the muta-rotation. Okay, then glycosides we have already discussed. Okay, anomeric carbon we have already discussed. Now, most importantly, I have to tell you about that when we talk about the sugars, okay, whether it is a alpha D form or a beta D form, we compare the structures of these sugars with the when I will make you study about the relative configurations. Okay, when I will make you study about the relative configurations. So these relative configurations are basically judged in respect to glyceraldehyde. Okay, let me show you. I'll change the link. Relative configurations of sugars, especially if we are talking about glucose. Okay, now see, the sugars, they are divided into two families. D and L, capital D and capital L. Okay, in 1906, Rozanoff decided that these two families are divided on the basis of configuration. Differentiated the two forms on the basis of their configuration. Right? Understood? So they are divided on the basis of their configuration compared to simplest sugar of those times, glycerol. Glyceraldehyde, ladies and gentlemen, it's a sugar having three carbon, so it is basically a triose. Okay, the basic structure is OH, CHO, H. Now, what you have to look here? Compared to the CH2OH, okay, compared to the CH2OH means this, okay. If what we have to look, we have to just look this primary alcohol, the carbon which is attached to this primary alcohol, if this carbon is having the OH, okay, on the right hand side, okay, this is the lowest asymmetric carbon, okay. So OH group on the right side of the lowest asymmetric carbon, okay. This is asymmetric carbon, OH group on the right side of lowest asymmetric carbon. So AOH is on the right side. It means it is what? The D form, capital D form. Okay. If we put a mirror, then we will get a mirror image. And as this carbon is asymmetric of chiral, and if the mirror image is non-superimposable, then they are known as what? Enantiomers. This is capital L form. Understood? Capital L form, capital D form. OH group on the left side. So this is D form and the L form. D sugars and L sugars. Okay. So these are D sugars and L sugars. Now, based on the number of rings, okay, based on the number of, when we talk about the rings, okay, so they are basically divided into two forms, okay, the pyranose form and the furanose form. So Fisher and Tollin proposed that the closed ring, that the ring of internal hemiacetal form, as we have discussed the formation of hemiacetal, is between C1 and C4. If it's in between C1 and C4, then they are furan type, and if it is between C1 and C5, then pyran type. Okay. So how, first of all, okay, he formed a ring between C1 and C5, okay, and gave the term pyranose structure. Okay, pyranose. In this pyranose form, what basically is done now, I will write a structure for you for alpha D glucose. Okay, I will write the structure for you for alpha D glucose. So first of all, I will make the alpha D glucose COH OH OH. OH. Now, these two carbons, carbon number 1 and carbon number 5, they are basically having this Okay, ethereal linkage. When they are having this linkage with oxygen. This is carbon number 1, this is carbon number 5. Okay. Now the groups which are on the right side, okay, with the white marking, they will come below the plane of the paper. So like this, OH. And the one who are on the right hand side, okay, they will come above the plane of the paper, H. Okay, simple, understood? So this is the first carbon, carbon number 2, again H, carbon number 3, OH, carbon number 4, again OH, carbon number 5 is attached with the oxygen that is having only just hydrogen, okay? H, and carbon number 5 is above the plane of the paper. OH, H, H, it is just above the plane of the paper. This is the fifth carbon. Okay, so this is the glucopyranose structure or pyranose form, and this is known as the Hout projection formula or pyranose structures. Understood? Same for beta you can make, but just for beta the OH will come on the top side, on the above side. Okay? So the groups on the right hand side of the fissure are on the left side of the or downside of the Hout projection. The groups on the right in fissure are down in Hout, and the groups on the left in fissure are up in Hout. Okay, we have done with this. So, ladies and gentlemen, we have completed the structure of glucose, the cyclic form of glucose, the pyranose form of glucose. We discussed about the properties of the glucose. Now we are going to discuss about the fruit sugar fructose. That is fruit sugar. Having a formula C6H12O6. Okay. So it is also known as fruit sugar. Okay. It is present in honey, and sweet fruits. Okay. Glucose along with fructose gives sucrose. It forms sucrose. Sucrose is a disaccharide. Okay. Understood? While fructose is a monomer for the formation of polysaccharide insulin. Okay. Fructose is the ketohexose or ketose sugar. It is a ketohexose sugar. Okay. So the polysaccharide. Okay. I forgot the name. Written the name. Inulin. The polysaccharide which is formed by the polymerization of fructose as a monomer is inulin. Okay. Fructose is levorotatory. Okay. And that is why it is known as levolose. Sorry. Known as levolose. Okay. It is a ketonic sugar as I have explained. Okay. It is obtained along with glucose by the hydrolysis of cane sugar. Okay. Obtained by cane sugar. C12H22O11. This is cane sugar. C6H12O6. C6H12O6. Okay, this is D-glucose. This is D-fructose. Now, structure of fructose. Okay, it is having a keto group on the second carbon. This is the open structure of D-fructose. Which is levorotatory. The minus sign is for levo-rotation. D-fructose. Understood? Same for fructose. We have a very important term which is known as invert sugar. Okay. So the solutions having equal molecules of D-glucose and D-fructose, they are known as what? Invert sugar. So first of all, I will make the cyclic forms, okay, for fructose. The cyclic form of fructose will behave like the same as of we discussed about the glucose, okay. The shifting of electrons, minus, plus, same, to form alpha and beta. This group come here. This oxygen will get attached to the acidic hydrogen to form OH. And then, so this is the first carbon, this is the second carbon. Okay. Now the third carbon, fourth carbon, fifth carbon, this is the sixth carbon. I hope you got it. So 1, 2, third, fourth, fifth, and so this is alpha D fructose. Same we can make beta D if OH is on the left hand side and beta D fructose. Okay. Now, if I'll make the Hout projection or the pyranose ring structure for fructose, then it will be okay. Here comes CH2OH, the first carbon, second carbon, and the fifth carbon is having. So basically, in the structure of fructose, the anomeric carbon is C2. This is the anomeric carbon, C2. Okay. So this is CH2OH, the second carbon. This is the first carbon, this is the second carbon, which is attached to the OH. OH, okay. H, OH. And this is the sixth carbon. Okay. So the attachment. Okay, one thing. I think I have done some mistake. This is the C2 of the keto group. No, the the attack will be like this. I'll make it again. No shoes. Yeah, this is the attacking side. Okay, everything remains same. Just becomes CH2. That's it. Okay. Yeah. So this is the alpha D fructopyranose form between C2 and C6. For glucose, it was C1 and C5. Okay. Now, what you have to remember that in free state, D fructose exists in a six-membered form. Okay. D fructose exists in six-membered ring, that is pyranose. Okay. In combined state in the form of disaccharide, it exists in furanose form, that is five-membered. Okay. Pyranose is six-membered and furanose is five-membered. Okay. In case of furanose form, the hemiketal formation takes place between C2, okay, that is the keto group, and the OH group of C5. Please remember, okay, that is the furanose form. Okay, so These are the two forms we discussed about, the pyranose and the furanose form. Now I will be talking about the disaccharides. Okay, there are some important disaccharides I have to talk about. Among the disaccharides are basically the carbohydrates. On hydrolysis, on hydrolysis, they give to either homo or hetero, same or different monosaccharides. Monosaccharides. Okay. Like we are going to discuss about the sucrose, which gives glucose plus fructose in the presence of invertase, maltose in the presence of maltase forms glucose plus glucose, lactose in the presence of lactase forms glucose plus galactose. Okay. Disaccharides basically they are originated when a condensation reaction of two monosaccharides takes place. Okay, to form a glycosidic linkage to form a glycosidic linkage. Okay. So monosaccharide units are linked to each other by the glycosidic linkage. Okay. The linking is just reverse of the formation of hemiacetals, that at hemiacetals they react with alcohols to form acetal. Okay. Sucrose. Some of its main properties. Most common disaccharide and widely distributed. Okay. In sugarcane and sugar beet. Okay. It is colorless, crystalline, and sweet substance. Highly soluble in water. The aqueous solution of sucrose is dextrorotatory Means it will change the plane of polarized light to right side or clockwise direction, having a positive specific rotation 0.5 degrees. Okay, but on hydrolysis with dilute acids or enzyme invertase, the sucrose or the cane sugar gives equimolar mixture of D plus glucose with a specific rotation of plus 52.5 degrees and D minus fructose with a specific rotation of minus 92.4 degrees. Understood? So in hydrolysis, the overall specific rotation comes to be levorotatory, and that is why on hydrolysis the specific rotation just gets inverted, and that is why it is known as what, the invert sugar. That is why it is known as what, invert sugar, or the reaction is known as what, inversion. Okay, just I'll make a structure of sucrose for you having the glycosidic linkage. I'll take the help of pyranose structure. This is alpha D glucose, and you know that fructose, when it is in combined state, it always exists in furanose form. Okay, this is oxygen, this is H, OH. The first carbon is above the plane of the paper, CH2H. There's the second carbon having H, having H. Okay, rest all you know. So here you can see the condensation reactions, the removal of water. Okay, the removal of water will takes place. Sorry, it's two, it's three, one, three, four, five, and this is six. So this results in the glycosidic linkage, and the final linkage after the removal of water, it comes to be like this. rest all stays same. Okay, so this is the linkage you can see. Okay, this is known as what? The glycosidic linkage. Okay, so here you can see the C1 of alpha glucose combines with C2 of beta fructose to form sucrose. Okay, the C1 of alpha glucose combines with C2 of beta fructose to form the sucrose. The glycosidic linkage is present between C1 of alpha glucose and C2 of beta fructose. Okay. In case of maltose, C1 of 1 glucose is linked with C4 of another glucose. In the glycosidic linkage is C1 of alpha D plus C4 of alpha D. Okay. In case of lactose, okay, which is known as what? The milk sugar. Maltose, it is known as what? The malt sugar. Okay, which is present in the sprouted seeds. Okay, so in case of lactose, C1 of galactose is beta D. Okay, plus C4 of beta D glucose. Okay, so C1 of beta D galactose, okay, and C4 of beta D glucose. They combines to form lactose. Okay, reducing and non-reducing sugars, I have already told you. Reducing sugars, they contain what? The alpha hydroxyaldehyde or ketone, alpha hydroxy ketone. Okay, now my dear students, I am closing this lecture. So our glucose or the carbohydrates is finished. Okay, we will be coming with many more videos. Till then, bye bye. Take care. Stay safe. Stay healthy.